Hi, today we are going to be looking at part one of the fundamental theorem of calculus. So if our function f of x is continuous on a closed interval from a to b and capital F at x is the antiderivative of f at x, then we can say the integral from a to b of f of x is equal to capital F at b minus capital F at a. So we're going to look at a proof of this. So let a at x be the area under the curve y equals f of x from a to x. So therefore we can say our ax is equal to our integral from a to x of f of x d of x. And essentially we have this curve drawn out. So we've got y equals f of x. Here's our a of x. Here's our starting value a. Here's our x. This point here we'd say is x plus h. This point here would be x comma f of x. Well, this point here would be x plus h comma f of x plus h. Now, if we take this theorem, or this formula, we can rewrite this as a of a is equal to from a to a of f of x dx. Now, if we're going from a and ending up at a, we know that that is 0. Where if we say we've got a of b, and that's our integral from a to b of f of x dx, and where AB is the area under the curve from A to B, we can then say that A prime of x is equal to our limit as h goes to 0 of A of x plus h minus A of x over h. Now this comes from our definition of the derivative. Now this we can then say is our limit as h goes to 0 of essentially our change in area, because this would be our area going from here to here minus our area from here to here. We can say change in area over h. Now that's going to be equal to our limit as h goes to 0 of essentially the area of this trapezoid. Now I've labeled out corners of this, so our trapezoid essentially is PQSR or PQRS divided by H. Now this is equal to our limit as H goes to 0. Of 1/2 times f of x plus f of x plus h times h over h, where this is essentially our area of that trapezoid. Now you'll notice that we essentially have an h here and an h here that can cancel. So that gives us our limit as h goes to 0 of 1/2 times f of x plus f of x plus h Now, if h is going to 0, that means we've got 1/2 times f of x plus, if h goes to 0, this is just f of x. Now, if we have f of x plus f of x, that's 2f of x, which when multiplied by the 1/2 in front, just gives us f of x. So we can say, therefore, a prime is equal to f of x. And as a result, we can also say, therefore, our area as a function of x is equal to f of x plus c. Now we can take this a bit further. We can say that when x equals a, we have area of a equals f of a plus c. Now, we earlier said that area of a was 0. So we can therefore say that c equals negative f of a. And if we combine that with what we had up here, we get a of x equals f of x minus f of a. Now, when x equals b, a of b is going to give us f of b minus f of a. So we can therefore say that the integral from a to b of f of x is equal to f of b minus f of a. Okay, so we'll utilize this to help us solve some integrals. So for example, we want to evaluate the integral from -1 to 2 of x cubed. So our integral of this would just be 1/4 x to the 4. And then what we tend to do is just put square brackets around. And then we'd put -1 here and 2 here. And essentially solving this, we would start with this final value. So we'd have 1/4 times x, which is 2. So 2 to the power of 4. And then we'll have minus, and then we'll have our value of this when we substitute in the -1. So we've got 1/4 times -1 to the power of 4. So that gives us 16 over 4 minus 1 over 4, giving us 15 over 4. Next example, we have an integral from pi to 2 pi of sine x. So we know the integral of this is just negative cos x. And we're going from pi to 2 pi. So we have negative cos of 2 pi minus negative cos of pi. Now cos of 2 pi is 1. We've got the negative in front, so that's -1. And then cos of pi is -1. Which will cancel out with this negative, giving us +1. And then we've got -1, so -1. So we get -2.